So last time we were looking at the Essing model, and we solved its partition function in the case where we have, just a reminder of what the Essing model is. It's a bunch of spins at lattice points that are either up or down. And we consider the case where it's an infinite chain. And the total energy, say the magnetic strength between any two nodes is J. And then we also consider the case where there's some external magnet with magnetic strength H. Then the total energy of this system was negative J. And then this little notation underneath the sum indicates that we're adding up over the nearest neighbors, which are ones that are adjacent to each other, of spins SI. And in this Hamiltonian, we're assuming that this external field is constant, is the same strength for every single point. So you can probably think of it, instead of this box over here, as like an infinite line, so that every single lattice point feels the same magnetic strength. That's SI. And here, SI is plus or minus 1. So this is the case where we solved the partition function, which we'll recall the partition function is the exponential of negative beta times a Hamiltonian, where beta is the inverse temperature of the system. Okay, so today we're going to look at renormalizing this case via coarse graining, which I'll explain in a second. But first, let's introduce some convenient notation. We're going to call K
I think
beta J.
You mean the sum over all configurations there for Z, right?
Oh, sorry. Yes. Correct. This is just like perhaps the Boltzmann of one case.
Right.
Yeah. So here we sum over all the spins in the partition function. Thank you. Cool. So we're going to introduce K to be beta times J. And we are also going to denote this sort of zoomed in case of an ith and jth spin. So I'm going to introduce a constant here, since it's going to pop up anyway. I'll explain that in a second. And then the strength over the ij from the external field is Si plus Sj. And then we subtract K, Si, Sj. So we can think of this as one part of the Hamiltonian. So the Hamiltonian will be a sum over these weights W. And this constant is here, since when we renormalize the partition function, it's going to appear anyway. Cool. So for renormalization, we desire a invariance in the partition function as we integrate over certain degrees of freedom. So what that means is that in our case, oops, I'm swapping notation there, sorry. If we have the spin at site 1, spin at site 2, S3, S4 along our lattice. I shouldn't have started in the middle with 1, because now I have to use negative numbers. So when we sum over, say, the even spins, So we'll keep the odd ones. We're going to end up with this case where we only care about, the only degrees of freedom left are the odd spins, and then we'll relabel this. So then we have, this is the new S1, we'll say the same. This is now S2, and this is now S0. So if this is indexed by I, say this is indexed by K. So this would be considered a coarse grain procedure where we consider the coarse grain length L equals 2, since we summed over every second spin. So therefore, in lieu of this, we are going to want to split our sum from the partition function, which is over every spin, into a sum over the odd and even spins, which I'm going to now switch to using sigma instead of S for spin. So we're going to have the even spins are sigma, and then we'll use sigma prime for the odd spins.
So there's a plus in between them, right?
Yes.
Oh wait, maybe I'm misunderstanding.
I think what I'm saying is we're just splitting. But yeah, you're right. We're just splitting the sum. I guess I'm writing it as a product, but we are just.
But maybe
the idea is that we first sum over the odd. And sorry.
No. I think it's right. It's actually a nested sum, isn't it? So
that's the idea.
The sum on the left is sum over functions assigning to every lattice point a spin, and then once you choose a way to allocate spins to the even sites, you still have to index over all the ways of assigning to the odd sites. So yeah, this is right. No, I was wrong. It's not a sum in between.
Yeah, I think the way I've written is think of it as like sum over all the odd one first, and then sum over the even one second, which should be the same as summing over all of them. That was present. So anyway, rewriting our partition function then, which is now this, and then like Daniel pointed out, I will now rewrite this in terms of the nested sum. I just realized that I write 1 to n. Yeah, I was wrong. That should be 1 to n on 2 of the previous board, sorry. Here he is.
That was weird. You're here now. Good to see you.
Welcome. This may not fit.
Hello.
Hello. Sorry, I wrote this down in terms of sigma, and I keep. Oh no, sorry, it is sigma. Yeah. Okay, so this term here, sorry, should be inside the exponential here. Do you want a quick recap, Alex, since it's still pretty early on?
Yeah, I would appreciate that. Thank you.
Okay, so if we look at the first board, sorry to walk into you there. So once again, I think you might have missed the last one, but we're looking at a model called the Ising model, which is on a one-dimensional lattice, which you can see at the top left there, which is just like a chain of lattice points. And at each lattice point, is associated a spin, which is either considered up or down, +1 for up, -1 for down. And the magnetic strength between any two spins is considered magnetic strength J. And we assume that notation for the sum, where it's got those those inner product brackets around it, indicate that we sum over nearest neighbors, meaning that we assume that the ith spin only interacts with the ith +1 and the ith -1. So just the ones adjacent to it. And then we also, it's common to include an external magnetic field called H, which is considered constant for each spin. So you can think of it as like an infinite magnet. So each spin feels the same amount of magnet strength H from it. Then the partition function is the sum over all possible states in this Hamiltonian. So we sum over all the spins of the exponential of negative beta times H, where beta is 1/t, which is the inverse temperature. Then we made a notation shift where we say K is beta J, just because it'll be useful later. And this bottom left weighted sum is just like a partition of the Hamiltonian. So if we sum over all these weights, that's the sum over all the spins. And then the top right, we look at now renormalizing it. So if we have our spins listed from -1 up to, I think I go to 4 there, we're going to sum over the even spins. So we're going to...
Sorry, what is C?
Oh, sorry, yeah. C is just a constant. That the reason we just introduce it there is because when we do the renormalization process, a constant appears anyway. And so it's common practice just to sort of shove it in there at the start.
And what is W? What is W?
Oh, W is just the function describing the right-hand side.
Yeah, I think it's just not clear from what you said why you're introducing that expression.
Yeah, that's fair.
You just defined this. Okay.
Yeah, I just defined this. Sorry.
And then this is H, and this is minus. Okay. Right. Okay.
Yeah. So
There's
this
just an expression like that.
Yeah. I do this because it will make, I think,
right,
the notation a bit shorter for rewriting later.
Right. Okay.
And then the top right, we sum over all the even spins on the lattice, which means we evaluate them as positive or -1, and then we relabel the lattice. So now we've got say if the first one here is an n length lattice, this is now, the K is now from n over 2. Cool. Right. And then we split this. So then what we've done, the bottom left, is so it's saying instead of summing over all spins, we're going to sum over the odd ones first and then the even ones. Sorry, reverse that. It should be the other way around. We're going to sum over the even ones, not the odd ones.
And what do you sum?
Yeah, I think that's a kind of confusing way of saying it. You're not summing over even or odd things. You're summing over configurations. So a configuration of the spins is the data of a configuration for the even sites and a configuration for the odd sites. And you can sum over those in a nested fashion. So first choose a configuration at all the even sites and then choose a configuration at all the odd sites.
Okay. Right. Okay.
Yeah, I think it's called integrating out the degrees of freedom. That makes more sense.
Okay.
Okay. Then we'll split our partition function.
Yeah, I think what you're doing in this first line here is a bit confusing unless you explicitly say that H is equal to the sum over I of W, S, I, S, J. And is that even what you really mean? What's the J doing there?
Sorry, what do you mean?
Okay, in the partition function, you're supposed to be summing over e to the minus, well, first of all, yeah. So you're supposed to be summing over e to the minus beta H. And then in that sum, you're replacing H by something to do with W's. Maybe you can write down on this first board what that expression is before you use it. No, not with Z, just like what is H? So what is H in terms of these W's?
Oh, the Hamiltonian, sorry. Right. I thought you meant the external magnetic field H.
Oh, right. No, curly H.
I was very confused. Oh my gosh, sorry, I keep switching notation. I guess it's SI is I plus 1. Okay, hopefully that makes it more clear. The only reason I'm really introducing this W function is because I don't want to keep rewriting the same expression.
Okay. And now there's a typo here because there's a J that doesn't mean anything.
Is that in the right-hand side of the opcam?
That's right. Yeah, in the first line there, it's WSI plus 1, right?
Yep, correct. Because you have the...
Okay.
Okay, I think we're good now. So now let's see.
So it's you're going a little fast somehow. So the key step here is something maybe you didn't say out loud. So you're summing over in the first line W of the S's, and then if you look on the first board, the sigmas and sigma primes are names for the S's at even and odd positions respectively. So then SI plus 1 becomes sigma prime I, sigma I, and then the next one is sigma I plus 1 prime, right? So it's just, these two lines are just rewriting things. It's not, he didn't really do anything. It's just expressing things in different notation. And now you're about to actually do something, I guess.
Yep, that's right. Hopefully maybe these green things help a bit.
Mm-hmm. Yeah, that's good.
These are prime. Okay, so now bringing down...
Is this supposed to be an equality sign? Or there's a second equality sign here?
Yeah, I think, it looks like it to me.
Yeah.
We'll just split the sum. Thank you. So what I'm doing now is I'm bringing down the sum from the exponential and then moving in the sum over the even sites.
Sorry, should this be as double sum in the second thing?
Yep.
This is from
Is this
Sorry.
Sorry.
Now there's like half a sum symbol.
Which where's the half a sum symbol?
Maybe something is wrong on my side or something, but I see like the top half of the sum symbol at the here.
Oh, okay. Yeah, no. It should be. I see the whole thing. That's a bug. Sorry about that.
Yeah, it should be a sum.
Yeah.
Oh. Wait.
Sorry.
What kind of
all?
Hey.
This was the sum. Okay, so
okay,
cool. So
I'm a bit confused here. So there's too many I's. Yeah. Yes. So this I, where are we? This I here became this I here, correct?
Sorry, I can't. Oh, sorry, in green. Yeah.
Yeah. Okay, but and then you're saying you moved this inside here. What is that? What you mean? How is that possible?
Oh,
Oh, no. That's fine. Yeah. Okay. No, I understand. Yeah. So if you take a product over I, and then for each I you choose either plus or minus one, then when you take, it's easier to understand from here. If you take this sum, you've got a bunch of products, and inside each one you've got something plus something. And so if you expand the brackets, you'll get a product over which factor you choose. Sorry to graffiti all over this. I will undo it.
It's okay. Yeah.
No, I hit my undo limit. Oh, I'm so sorry.
That's okay. I think it's.
I'll erase them. Oh, that's so rude. Okay. I thought I was confident in my ability to undo.
It's probably not as bad as doing it on a real board, I guess.
There we go. That's kind of okay. All right. And then let me just check I understand the exponent. Yeah, okay, that hasn't changed. All right, cool.
Yeah, that hasn't changed. Okay, so one of the assumptions of renormalization is that the partition function has to remain invariant. So this new partition function we want to make, which has n over 2 spins, has to be the same as the partition function with n spins.
Yeah, what do you mean by that? That's a very confusing statement at first glance, right? So the partition function on the left, first of all, the partition function is just a number, right?
Yeah, sorry. I guess I should say it should have the same expression. Like it should be able to express in the same.
That's an even more confusing statement. It's a function, I hope, not just a number.
Yeah. Well, what's the partition function a function of? A priori, it's just a number. You sum over all configurations the energy. Now, of course, you can restrict the manifold of states you're allowed to integrate over, so the partition function will be a function of those choices you could make to restrict the set of allowed configurations. Among other things, you might put parameters. For example, it is a function of the inverse temperature, because you're summing over e to the minus beta h. You could vary beta. So there's all sorts of things inside the exponent you can vary, and it's a function of all those. But then, right, so in what sense are they the same? Maybe it's better to do the calculation, and then we can argue about what the equality sign means.
Yeah. So what I've written here is so the partition function of n over 2 we want to look like this, which you'll notice is pretty similar to the I forgot the negative beta. Sorry. Which is pretty similar to the Zn on the other board over here.
Well, I don't get it. Doesn't the Zn2 just have n minus... Sorry, the Zn over 2 describes a system with n over 2 sites.
That's right.
Yeah. Why would that be equal to Zn?
What I mean, I got told once you shouldn't leave incorrect things on the board. I think like what Daniel was trying to say is that you expect the partition function to have, I don't know if it's the same structure is the right way to say it, but
to be from the same class of systems, but it's on fewer sites. So these are genuinely a bit subtle issues. So if it's an infinite lattice, they're literally Hamiltonians for the same kind of system, right? Now in this case, there's different numbers of spins, so the state space isn't even the same. So what the hell are you trying to do? It does make sense, but it requires some explanation. Maybe, I think it's better just to start from the Zn and continue with the calculation and then end up with something that looks like this and then say something rather than say this at the beginning. Because the actual thing you're aiming at it's like well defined at the level of how physicists talk about it. So I'm not saying it's this is how a physicist would present it, but I think it's going to give Alexander conniptions. So let's.
Yeah, I didn't get
let's
this one
do
from
the
this textbook, so
yeah, just do the calculation, and then it'll be on the board what we're saying, and then we can like articulate what it's saying rather than argue about it. Before
I guess to me it seems simpler to like say we're looking for this so that when I pick some stuff, it doesn't seem like such a magic trick. But I guess,
okay, so let's put that in scare quotes or something.
Yeah.
Here, big red scare. That's right. Yeah. No formal meaning yet.
And then in more scare quotes, what we want. This W prime, sigma I plus 1 to look like. Will also in scare quotes want to look like the oops, that's kind of illegible. This is a K, and the K is, remember, beta J. Okay, so let's walk over here. Oh, I think you might be a little bit in the way there, Alex, sorry.
Yeah, your head's in the shot, Alexander.
Hopefully. Oh my. Sorry, the iPad just locked itself. Oh, here we go. I don't know how I did that. Okay, so what we want now is this thing to be, I guess, scare quotes equal. Oh no, people put like an exclamation mark, don't they, in front of stuff like this?
It's okay. We don't need two sets of scary things. I think just you can go ahead with the equals.
Okay. I'll just redefine my equal sign.
This is the stuff inside the bracket 2 boards ago, right?
Yep. I'm just expanding it a bit to, hang on, sorry, let me finish before I, okay, so this thing under here, this is
Are you not missing
W.
Are you not missing a beta?
Oh, yeah, I am sorry. I didn't write the beta down when I did the calculation. And so every time I look at my notes, it's not there.
And I think maybe also there's also a sign issue somewhere, perhaps. Is it a minus? Yeah, oh, you'd put minus beta. Yeah, okay.
Yeah, the minus beta is up the front.
Yeah, so just to be clear, if we go back 2 boards, then the stuff I'm underlining in green is what you just expanded, right?
Just walk back. Yep. Yeah, that's exactly right. I'm just like using the definition of W. Okay, cool. So now I'm going to define some new variables, which will make.
So again, to be clear, this is what we want to choose. Like we hope to be able to choose C prime, H prime, and I guess you're missing a prime on the previous page. K prime is beta J prime, I guess, right?
Yeah, we want to pick the primes to make this thing true.
Yeah, ideally, at least approximately.
Yeah, up to a constant factor, I think is.
Because if we can do that, then we go back 2 boards ago and replace that term inside the brackets by an exponential. Then we'll be close to getting the form on the top of the left-hand board.
Yes. Okay, so using these, so substituting these expressions for x, y, and z and x, y, z primes into this expression above, I can write this as z prime, y prime. This is to the power of sigma I plus 1 over 2.
Wait, where did
X
the h...
prime.
What are you writing down? Where did the h prime come from? I don't know what this expression is.
Where did it go, you mean?
No. What are you writing down right now? I have no idea.
On the right-hand side. This is, so on over here, I defined these new variables. And so I guess maybe, yeah, I'm splitting I'm using the exponential to I'm using this. So I'm factoring out factorizing the exponential. And then I'm using these definitions that I've.
Oh, I see. You're just rewriting the previous equation in terms of...
Yeah, that's right.
Okay.
Yeah, I'm not doing anything too magical. Sigma I plus 1. So that's the left-hand side. And then the right-hand side will be a sum over sigma I is either plus or minus 1. Z squared y to the...
The beta disappeared again, I'm guessing.
It did. Sorry, all these definitions I wrote on the left-hand side should have a beta at the front.
Yeah.
Where did negative beta?
Where did the 2 come from? Oh, there's 2 C's inside the bracket. Yeah, okay.
There's 2 C's, yeah.
Okay.
Yeah, the Z's are just a constant, so we're not going to really care about these ones too much. The ones that we care about will be the X and the Y's.
Okay, am I just giving up on the beta, or are you going to put a beta inside your Z's? Yeah, so you should probably... Where is the beta supposed to live, really? Should it be like Y is e to the beta H?
Yeah, there should be a negative beta inside all of these.
Okay, I'm kind of scared now, but all right. Mm-hmm.
Yeah, because the negative beta should be here.
Yeah, right. That makes sense. Okay.
Yep. Yeah, I really should have.
Okay.
This will be to the power of sigma primes sigma I, and then this is all times y. Just 1 prime over 2, and then x to the sigma I prime plus 1. Okay, so now
again, this is an equation we're trying to solve still, right?
Yep, exactly. So I think the simplest way to go about this is, sorry, Alex, yeah?
Yeah, I'm pretty lost, I guess. I'm not even sure. Is it, you said Zn over 2 to be equal to Zn. Oh, no. Did you remove that? No?
Yeah, it's kind of lurking here still. But
that is still lurking here. I think the thing that I want to impose is on the OrbCam on the top right hand side of the board now. So I want the exponential of this primed thing to be equal to.
Wait, there's a cam. Wait, I can follow some cam. What does that mean?
Oh yeah, click OrbCam in the top.
Yeah, click on OrbCam, and then you can see. And then if I move, you can follow along.
Oh, and my head is in front. Okay.
So
that's interesting.
Yeah.
Okay.
Yeah, come back over here, Ben, to this board. Right. So Zn, the partition function, this is the crucial equation. This is what he's working on. So he's looking at this, and he nested the sum over all configurations into a sum over configuring half the spins and then the other half. And then he's operating on this inner sum and trying to turn it into something that looks like he wants to get rid of this and have something like e to the minus beta stuff.
Yep.
Because then this whole sum will look like sum over a configuration of half the spins and some effective energy for that half, for those.
Right.
And that's the renormalization step. So then he will have expressed his system approximately in terms of half as many degrees of freedom. So the whole game is to take this sum and make it look like e to the minus beta something.
Right, okay. Right.
And to do that, he's looking inside this product and saying, forget about the product for a moment. Let's look inside this and try and do something with this exponent. And that's then what... Okay, forget about this next board. I think that's kind of confusing, but the second to last one is...
So you take out... You have a product there as well?
Yeah, there's a product. That's right. So the product will kind of take care of itself, I think. What he's worried about is that sum inside the bracket. So the sum over sigma I equals plus or minus 1, e to the minus beta something. That is what I'm now underlining in, what I'm now circling in red on the second to last board. This whole term here is what is inside that bracket underneath the product.
Yep.
And so he's going to try and write this as e to the minus something.
But it's already e to the minus. Oh.
No, it's a sum.
There's still a sum up front.
Uh-huh.
So the problem is if you evaluate the sum as is, it's e to the something plus e to the something.
Now, of course, he's being more precise than just e to the minus something. He has in mind that it's minus beta this, but this is the something. So we could even take this as a second step.
What is the prime? There's sigma and there's sigma prime.
So sigma prime was so if we go back to this board, sigma prime is what I'm relabeling as the odd. I'm labeling the odd spins as sigma prime and the even spins as sigma unprimed. And then the sigma primed ones are the ones that are going to stick around after I do the renormalization step.
Right. Okay.
Yes.
Yeah. Okay.
So, and then what I've done here is to make the expression simpler to write, I'm defining these x primes, y and y primes, z and z primes. So then that thing on the left-hand side becomes this thing on the right-hand side.
Yeah.
And so now, if we consider the case where, so there's only 4 cases really. Sigma prime can be either plus or minus 1, and the ith sigma, so I'll write it down. So sigma prime I is either plus 1 or it's negative 1, and then sigma I plus 1 prime is either plus 1 or negative 1. So in the case where they're both positive 1, the expression above can be written as this. And then I'm also evaluating this sum in this step as well.
I lost track of what's determining the prime.
So all I'm saying here is...
There's an outer sum over the prime configuration. So, yeah.
I think, yeah. So all I'm saying is there's only 4 cases that these sigma prime values that these sigma primes can take. Yeah. And so evaluating all of them will allow me to solve for x, y, and z. It would give me enough equations. X to the negative 2, y to the negative 1.
This is actually quite, this is extremely crucial. Effectively what you're defining here is the map from the coarse-grained configurations to the fine-grained ones. But it's it's kind of implicit. But yeah,
That sounds like physics. So it's a y prime to the power of -1.
Just flagging, we'll have to stop in 10 minutes.
That's okay. I think I should be able to get through. Let's walk over the next bullets though. So once we evaluate the next two cases, then then we'll have 4 equations to solve for 3 unknown. Well, actually, sorry, it's not true. We'll have 4 equations and I guess 6 unknowns, but since we only solve up to a constant factor, we will see it's fine. So third case, this is the one where sigma prime is +1. Actually, the fourth case is going to be the same as this one. So this is going to be an identical equation.
These are all meant to be primes. Yeah, okay. You put that prime in.
Yep.
Okay.
Yep. That's right. And then the last equation is going to be s prime x1 prime to the -1 y plus a half. Okay, so now we have 3 equations that we can use to solve this. Well, solve for the z prime, y prime, and x prime. So if we take all 4 equations and multiply them together, we get z prime to the power of 4 is equal to z to the 8, y plus 1 to the -1 squared, x squared. I'm sorry. X squared y, x to the -2, y to the -1, x to the -2 y plus x squared y minus 1. And then if we, so this is multiply all 4 together. And for the second one, if we divide the first one by the second one, we get y prime squared is equal to y squared x squared y plus x to the -2 y to the -1 over x to the -2 y x squared y to the 1. And then finally, if we multiply the first 2 and then divide by the multiplication of the next 2, we then get x prime to the power of 4 is equal to x squared y squared plus x to the -2 y to the -1 x to the -2 Okay, so implicit inside x prime is k prime. This is e to the -beta k prime. And so if we take the logarithm on both sides of this expression, we're going to get 4k prime equals, that'll be a minus beta at the front of both.
Yeah,
which I'll be able to count.
I think you don't have to write it again. I think it's,
yeah,
it's fine.
I'll, and then this will be equal to logarithm of e to the 2k plus h plus e to the minus 2k minus h. Okay, now, if we consider the case where there's no external magnetic field, and so we'll just set h to be 0, then we'll end up with the expression 4k prime is equal to log of 2 squared cosh 2k squared, so I'll just use the logarithm rule on the first two, minus log 4, which then gives k prime, if we rearrange a bit and simplify, to be a half log cosh of 4k. Oh, and I also use, sorry, kind of skipped that a bit. And that shouldn't be a 4, that should be a 2.
Yeah, I've seen stuff like this before, I think, this cosh stuff.
Yeah, this just comes from that. And so, sorry, just to finish off. So this k prime is the degree of the parameter of the renormalized Ising model, which is, remember, equal to, no, sorry. I think the beta was inside the k the whole time. I just realized, because it's beta j. I think that's where it's been.
Well, it doesn't solve all the missing betas, but maybe it solves a few of them. Right, so you've now found the equations which, modulo some details that are left implicit about exactly in what sense Zn and Zn on 2 are really the same thing. You've found parameters for this smaller Ising model, which you're then going to claim you can iterate. Of course, you can't if it's finite. You'll end up with dividing by 2 too many times. But in some sense, what you're really doing is talking about the infinite system.
Yeah, that's right. It's an infinite chain. Sorry, I forgot to mention that. Even though we would take n to infinity. So the idea is, if you plot your new parameter k prime against your old parameter k, so say you pick a point along this function, and that's your k prime, then your new parameter becomes k prime, which is there, and then you input k prime as your new input, and then you kind of repeat this iteration step. And so the RG flow in this case heads towards the origin. So the origin is a fixed point where k is equal to 0. And I think unless k is equal to infinity, unless k is equal to infinity, it flows towards 0, which is considered like a high temperature.
Yeah, to be clear, k equals 0 means that the spins aren't interacting, right? They just fall in.
This is very high temperature.
Yeah, we're going to have to stop there because I need to go to the next seminar. But that was great, Ben. Thanks. Yeah, I think maybe I'll come back on some of these points Alexander was asking about. Maybe in a future seminar, we could probably spend at least half an hour digging into exactly what this calculation is saying, but I think seeing it from beginning to end like this is it's instructive.
Yeah, it is very much a physics calculation.
What's the next seminar?
AI safety. So Elliot Catt from DeepMind, he's a former student of Marcus Hutter, and in Marcus Hutter's group there will be speaking about their work on AGI. Well, AI safety.
I can't believe you're going to make me stay at uni till 10 p.m. because that sounds really fascinating.
Yeah, but we better go, otherwise I'll be leaving him hanging. So thanks, Ben.
Yeah.